All right. So there's basically, a couple of different topics. There's really, I guess, really kind of three topics that we're going to talk about. Um, First order differential equations, second order differential equations, and then numeric solutions. So I say numeric solutions. What do I mean by numeric solutions? Do you know what that means? Yeah. Approximating the answer, which is actually a heck of a lot more sensible of a thing to do, as it turns out. Why do we do differential equations? Well, you need some intuition about how dynamic systems behave, which I'm going to talk about a little bit today. All right. But in reality, for a lot of stuff about calculus, I mean, calculus, you needed all the closed form solutions to everything back when Sir Isaac Newton was doing it. But nowadays, a computer can do most of the work fairly well, right? And so it's more important to me that you really begin to understand some of that stuff. Now, when I say computer approximating it, that means we got some MATLAB stuff that's going on too, right? So this is one of the last things that we'll do before the first project. All right, so you remember, basically there's five major milestones for grading, right? So exam one, the second one is project one. All right, project one will be coming out shortly after the exam. All right, and it's going to be focused on a lot of numeric work. All right, so more to come on that. So for today, I want to focus on these, and again, these are the sections in the book where it covers each of these. But basically, two topics that I'm going to talk about here. So today, what causes differential equations? Like what gives rise to them physically? Because that's what matters to me, is what are they, is physically what they mean. All right. And then first order differential equations. So first of all, if I use the term order, what does that even mean? Hopefully you've heard the term first order and second order differential equation. What's order? Yeah, so if I have a differential equation that has a first derivative only, that's the first order. And if I have one with a second derivative, it's the second order, right? Now, that's the math way of thinking about it, right? For me, I like to think of that more from a physical perspective, because from an engineering perspective, it's got to mean something physically, right? I think of it as what? Basically, I think of it as, if I have a first order system, I have one energy storage element in a system. If I have a second order, I have two energy storage elements. So if you've gone all the way through 2111, what are we talking about if I have a first order system? I have a single what or a single what? A single R, well, a single L or a single R. All right. In the case of other systems, I can have other sorts of energy storage elements as well, right? So why does it matter? And they matter for both electrical and computer engineers. And the computer engineers never want to think that anything with math matters, right? But it does, right? For a lot of systems where you're actually applying this stuff, right? So circuits, we have dynamic systems, right? So L's and C's. But the other thing that you deal with a lot would be electromechanical systems, right? So any kind of a system with a motor where you're driving some kind of a vehicle. So automotive examples, autonomous vehicles, right? An electric vehicle, any of those sorts of systems, there is some sort of dynamics to it. All right. Now, I've used the term dynamics before. What does dynamic mean for a system? It changes with time. All right. It changes with time. All right. If I had this system right here, would you call this a static system or a dynamic system? Static. Now, there's one exception, I guess. If I say a T equal to 0, I basically clicked the 9-volt battery into that circuit, right? Immediately, as soon as I hooked up the 9-volt battery to this circuit, what would the current in this circuit be? Given the components that I have there. Don't give me a number. Don't worry about a number. It's what divided by what? So yeah, 9 divided by 3,000 plus 10,000 plus 5,000. All right. I worry less about numbers and more that I can see that. All right. So when I look at that current is that as soon as the battery is connected. Right. And it doesn't take any time. Now, in reality, it wouldn't exactly happen that way. Right. Because all systems have some inductance and whatnot. But if I truly just had resistors like that, the current would immediately be that. I call it a static system because there's nothing that changes over time. Now, there, again, this is an approximation. This is a model. If I actually truly had a 9-volt battery and those resistors, what do I know about a battery? Well, a battery is actually going to discharge over time, right? It's not, doesn't have infinite energy in it. So yes, things would change. But if I had a perfect battery and perfect resistors, this was a static system. If I, on the other hand, had a capacitor and a resistor, or even more simply, my little box with wheels here. This is a box with wheels that is a car. It has a mass M. Okay. Let's say that guy is moving a certain direction, right? If I take a car and I accelerate a car from stopped, right, it doesn't immediately go up to 70 miles an hour, right? It builds slowly. Why does it build slowly? Why doesn't it just immediately jump up to 70 miles an hour? Well, sure, but why doesn't it just accelerate infinitely fast? Why? Because of the mass, right? That mass stores energy. And I can't immediately. So what's the energy stored in the mass? Let's think of it like that. There's energy that's stored in that guy that you learn that in physics. What's that? In physics, they often use the term W for work. No, I don't want to do that. I don't want to get nerdy. Let's say it's energy. What's the energy? Einstein over here. Right? So if I'm talking just regular physics here, right? So this guy is a mass M. What's the energy in the mass? And it's moving at a velocity. What's that? 1/2 mv squared, right? That's the energy stored in a vehicle that's moving at a velocity v and has a mass m. Because that mass represents energy, that energy storage element, right? So the way I think of this is the mass is an energy storage element. The velocity is sort of the thing that it's storing, right? But because of that mass, I can't immediately make this thing go from 0 to 70 miles an hour. I have to charge up effectively. I have to get the energy stored into that vehicle. So I cannot instantaneously ever change energy from 0 to something instantaneously. I can try to, but what happens if I do that? So like, for instance, what happens if that car going 1/2 mv squared hits the wall all of a sudden? What happens to the car? It blows apart, right? Why? Because all of the stored energy inside that thing can't immediately go to 0. So it's got to go off into motion of parts flying all over the place, right? If I take a capacitor, or better yet, you've probably seen this, right? If I have an inductor, right? If I have an inductor, so a good example of this would be, let's say I had a hairdryer that was plugged into the wall, right? And it was going full blast, and instead of turning it off, you pulled the plug out of the wall. What happens if you pull the plug out of the wall like that without turning it off? It can't, because there's no current flowing anymore.
But like it has a fan inside of it, right?
That fan will stop. I mean, the fan might be moving still because it's got some stored energy in it. But if you look at an outlet and you pull a plug out of an outlet real quick, sparks. You'll see a spark. What's the spark? Well, because in that circuit that you've got, there's an inductor and there was some current in that inductor, right? So you learned in physics, right? 1/2 Li squared is the energy stored in an inductor. If I make the I go from something to 0 instantaneously, the energy that was stored in that inductor has to go somewhere, right? So where does it go? It becomes light, right? Same thing's true with a capacitor. If I charged the capacitor and then stuck a screwdriver across the terminals, what happens there? Well, it'll spark on you. I mean, it's going to discharge, yeah, but it'll spark as soon as you do it if you stick a screwdriver across it. Because the energy stored in the capacitor has to go somewhere, so it becomes light. All right, it's got no choice as to what to do. So what that's saying is if I have an energy storage element, I cannot change its energy instantaneously. It takes time for it to change. All right, it has a sort of a trajectory from one state to another. So if I had a capacitor like I have right here, let's say this capacitor was charged up to 5 volts. So 5 volts was equal to the capacitor voltage at time t equal to 0. What would happen? What would eventually be the capacitor voltage in this circuit? Trick 2111, you should know that. The capacitor voltage at t equals 0. What is it? Well, t equals 0, I just told you it's 5 volts. That was a trick question. All right. What is it at t equal to infinity? 0. It's going to discharge, right? What's happening? The energy stored in the capacitor is basically being lost in that resistor. And if that resistor was 0, it would be gone immediately. But what's going to happen? What will it look like over time if I looked at that voltage on that capacitor? So it'd start at 5 volts, right? And then at t equal to 0, whenever I close the switch or whatever, what would happen in this case? And how, yeah, what would it look like? Yeah, it'd be an exponential with a negative exponent to it. Yeah. This would be end up being 5. And we're gonna derive stuff like this, but e to the negative t over tau, whatever tau is, right? That would be what the voltage on that capacitor would look like. All right, we're talking about what tau is in a second, all that kind of stuff. If I took this, so I'll call this the capacitor voltage, V sub C. If I looked at the velocity of this car versus time, and it started out at 70 miles per hour, what would it do? If I just let the gas off and I was on a flat road, what would it do? It would coast, and it would slow down exponentially, right? And I would see it happen basically as 70 e to the negative t over tau, where tau is something. I'm approximating it. Probably wouldn't be perfectly like that, but it would be really close to that. All right. So any system where I've got energy storage, whether it's a mass, whether it's a capacitor, whether it's an inductor, whatever it is, right? I'm going to get these sorts of behaviors, these exponential behaviors. And what it represents is the fact that I cannot change the energy in a component, an energy storage element, in 0 time. It takes time for it to evolve from wherever it starts. So from one steady state, this is the way I think of it. This is one steady state condition to another steady state condition. What's going to happen in any of these systems is there's basically going to be an initial steady state and a final steady state. And this exponential behavior kind of tells us how it evolves from one steady state to another. All right. And that's the part that we call the transient response of this system. All right. And that's the part that we're going to be focusing most of our time on. So, what I was saying in this case, right? So dynamic systems, basically anywhere I got energy storage devices. So electromechanical systems, an example, L's and C's. We come across this in embedded system controls a lot. So when I talk about embedded systems, oftentimes I'm talking about controlling a motor, let's say in a robot or something like that. There are essentially energy storage elements in those things. If I'm a controls engineer, I probably do need to know something about differential equations because the systems that I'm controlling, if I'm controlling a robot or something, has in it some dynamics. And so I need to understand this stuff. We use it a lot in simulation. So one of the things we're going to do is some circuit simulation in the project. And so, it's a programming problem, and there's a lot of stuff to it. We even kind of see this when we get into looking at circuits a little bit, right? Anyway, we are talking about, like I said, hand solution, how we kind of work out the solutions. But one of the things that I'm really, kind of concerned about is that you guys getting an intuition about whether things look, whether a system looks first order, what's it mean to look first order? What's it mean to look second order, right? So why do we stop at second order? I could have a 20th order system. Why don't we keep studying third order, fourth order, fifth, sixth? It turns out pretty much everything can be thought of as either first or second. All right, and so we need to understand those kind of two basic behaviors. And it's important to me that you get kind of an understanding of if you look at a circuit's behavior or something like that, you could tell me whether it's first order or second order. If you know it's second order, you know what it might look like. Okay. All right. So we talked about this a little bit, but just to summarize, right? If I've got dynamic systems, there's always going to be two parts to the response, right? There's going to be the steady state response, which comes directly from whatever the input to the system is, right? So in the case of an RC circuit, if I have a voltage source, that voltage source drives the steady state behavior, okay? If I have, the other part of my response is basically reflects how much time it takes for the energy in the system to move from its initial condition to its final condition. All right, I call that typically the transient response. The terms that are used for that are sometimes the homogeneous, the complementary, or the transient response. You see all three of those used. To be consistent with what they do in the book, I typically will call this part of the response with a sub C, complementary. They tend to call it that way. The steady state response, in differential equations, what do they call that? You guys remember? Typically. You said you took differential equations. What do you call the steady state response in a differential equation? For the third time? Yeah, sure. What do you call the steady state response to a differential equation? No, we just said the homogeneous is the same as the transient one. Was it? Particular. Yeah, that's the term that's often used. Yeah. All right. So homogeneous in math terms, they usually say the homogeneous or the complementary for the transient part, and then the particular for the steady state part. All right. And we're going to walk through those today. Now, I said it even matters for computer engineering things. So let's look at this. Let's say you had this system right here. What is that system? What are those things? Inverters. What's an inverter do? Yeah, it basically takes a 1 to a 0 or a 0 to a 1, right? So if I think about how those things actually operate, let's say VI, my input here, let's say it looks like this. All right, so it goes 0, or so it starts at 5, goes to 0, then goes back to 5, and let's say it just repeats like that. I have a little clock waveform that's going up and down. What would VO look like? What should it look like? Should look like the inverse of that. So it should be low, and then it should be high, and then it should be low, like that, and it should continue. Now, in reality, what it will actually look like, all right, so I try to do this a little bit separately here. So this is what they should look like, VI and VO. This is what they will actually look like, right? So VI looks like it should, but VO looks a little bit rounded. Why is that? Why do I see a rounding here? Well, and specifically reason it takes time to change states, like what I'm showing here, right, is if I looked at what an inverter is, the inverter basically is connected to the next inverter in this particular case. And so there's current that runs down that wire, goes through this thing, and then goes back this way. So ultimately, there ends up being some capacitance inside this. It's made with chips, and there ends up being a capacitor basically inside this chip. All right. And so there is some capacitance that exists here, basically. And so if I could actually model this thing and say that there is essentially some element of capacitance from here to ground. All right. That stuff matters because if we talk about like how fast a digital system can operate, it's limited by things like these capacitances. And in reality, there's probably even some inductance to that wire. All right, which may cause problems. And why does this matter? So the reason it matters is I get this rounding effect, but it tells me that I can only make that clock waveform, that input waveform, be so fast. If I make it too fast, I might have a problem, right? Because of how long it takes for that rounding, right? So that impacts chip design, is basically what I'm trying to say, right? I need to think about how I design a chip because thinking about these sort of parasitic elements. I call them parasitic because I don't intend for there to be a capacitor there, but because of the way I have to build it, there is a capacitor there. All right. And that's one thing that we talk about a lot, right? And I don't think you guys fully appreciate it, but like this circuit right here, if you look at that circuit, yes, there's 3 resistors and 1 battery. Right? If I built that in the lab, I would have 3 resistors and I'd have some wires. If you guys built it, your wires would probably go like this and then come back down, right? It'd be huge wires, right? Those wires have inductance, right? And so this is always just a model for whatever you actually build. All right, that's probably the most important concept in engineering at some level is there is what you build and there's what you model. And they're never the same. But the question is the model good enough to capture what's happening in the system? All right, at some level, the model for a voltage source and 2 inverters can be just that. At some level, maybe sometimes it matters that I model it as having these kinds of other components, right? Part of what you're really kind of learning in all your classes right now is just the basic analytical tools. But as you get more advanced, you start thinking about how do I apply those analytical tools to model real physical systems, all right? That's what we're really trying to capture in classes like this, is how do we get the analytical tools to make those models, all right? Where you make the big bucks in the world, engineering really kind of comes down to, can you build models that really capture what these systems are doing so you can understand them, okay? All right. So for us, for right now, we got to focus on the mundane stuff, though. I basically got to focus on, if I get a differential equation, how do I solve that differential equation? All right. All of my homework problems on this are going to follow the same basic 3 steps. All right. Step 1, solve what I call the homogeneous equation, which gives me the transient response, which we are going to call in here Y sub C. All right. But I may say homogeneous, transient, complementary. Use all those terms. I typically tend to say the transient. All right. Y sub C, we'll call it. Then I solve what I call the non-homogeneous equation. All right. That's just the equation. All right. We're using fancy math words, but let's say I give you A times dy by dt plus B times y of t equals C. So A, B, and C are all constants. This thing is what I would call the non-homogeneous equation. Non-homogeneous equation. All right, what's the homogeneous equation? Differential equations was a fun time, huh? What's the homogeneous equation? That's the non-homogeneous. Where it's equal to 0. Okay? Where it's equal to 0. So basically, the non-homogeneous is this one. The homogeneous would be if I said the same equation equal to 0. All right. And there's a reason why we break it up into 2. And I don't spend a whole lot of time talking about it. But basically what we say is that our solution Y is the summation of the 2 solutions. Now, I don't want to go into I don't spend a whole lot of time in the details of derivation. All right. You can look up the derivation of this in the book. But basically, by the principle of superposition, all right, I can effectively say that if I plugged in these 2 solutions together, I would be solving that equation, right? Where it's basically solving the non-homogeneous, and the homogeneous basically is if I added it to 0. Because whatever solution I put in here for that equation, the homogeneous one, equals 0, right? And so I basically, it doesn't change the solution to the other one. Now, why do we end up doing 2? Well, because the homogeneous one, the non-homogeneous one, which is the original equation. I hate the terms, right? If I solve the original equation, I'm going to get the steady state solution. It doesn't capture the transient piece. I have to solve the homogeneous to be able to get the transient piece. All right. So we're going to do that here, right? But this method always works. And we refer to this methodology, right? So what we do is we use what's called the undetermined coefficient method when we solve this. All right. You guys learned that. Chances are you probably say, oh, I like the Laplace transform way of doing it. All right. Laplace transforms are important. But we're going to be focused on this method, which is basically where I guess the forms of the solution, right? And then I basically have to fill in some blanks in my guesses. All right. So couple of things. The equations that we deal with always look like what I have right here. All right. So it's a non-homogeneous differential equation with constant coefficients. A lot of math words. What's that mean? Well, constant coefficients. What does that mean? Looking at that thing. What does it mean to say constant coefficients? Yeah, the coefficients themselves don't change with time. For most real systems that I have, like RC circuits and things like that, it's the R's and the C's and the L's. It's those values that basically give me the coefficients when I do my circuit analysis. Better be the case that the R's and the L's and the C's don't change over time, or else becomes an ugly system to deal with. All right. So if we say they're constant, we mean the coefficients basically are just numbers. All right. Could be complex numbers. All right. And we'll see that. There's a lot of systems where they are complex numbers. This thing over here is what I call the driving function or the input. It should always be the case that if you guys are doing a circuit like in 2112, the input source, whatever the voltage source or current source, better end up on one side of the equal sign. All right. That's always going to be the case for your problems. Okay. All right. So most of our, everything comes from physical system, looks like this. An important point that I always make is there's always as many derivatives as there are energy storage elements. Okay. So if I have an RC circuit with one capacitor, first order. It's an RL circuit with one inductor. It's a first order system. If I have an RL circuit with two inductors, I can basically combine those to be series or parallel inductors, and I can think of it as one, right? If I have an LC circuit, that leads to a second order circuit because there's an L and a C, okay? All right, so basically the important thing for us, if we're talking about systems that we deal with in our types of systems, our types of circuits and whatnot, we're going to have differential equations with these inputs. So either the input, and the input meaning, this guy here. So I'm trying to link the math with what you see in circuits, right? And again, on the project, you will see that. I give you more real systems to worry about in the project. I'm worried about applying this stuff. The inputs that I have are typically going to be of these forms, okay? It's either a constant function of time where x of t is equal to some constant. In other words, a 9-volt battery, right? So that's a voltage source, and it's constant. Sine waves. I said sine waves are really important for us. We have sine waves all the time, right? So we'll have that stuff. We might have sums of sine waves, okay? Or we might have exponentials. And based on what we know, I can actually say something pretty important about all four of those. They're all the same, aren't they? Aren't all of these some form of an exponential? Right? I can say that basically all of these are basically C e to the, I'm going to say st, where s could be, in this case, what is s? S is 0. In this case, I don't know, s is some complex number. S is complex. S is complex in this case. When I say S is complex, what am I doing with this guy? I'm saying that x of t, if x of t is equal to c cosine omega t plus phi, I'm saying that can be thought of as what? How am I thinking of that guy? If I have a cosine, it's what? Real part of what? C e to the j phi times e to the j omega t. All right. Again, ugly. We're just gonna make the math a heck of a lot easier ultimately in this stuff. All right. This is one of the reasons why we do it, is it makes the map a lot easier. Makes it weirder, but easier. When I say weirder, it makes it weirder because we're using imaginary numbers. It makes it easier because it gets rid of differential equations altogether for the most part, which is what's nice about it. All right. So basically what I say is with all of these inputs, right, I can think of all of these as special cases of the exponential, right? If I have c e to the at, I can think of it like this. All right, that last one there, I wrote it a different way, but it's entirely the same thing as saying what I just said. It's the real part of c e to the j phi e to the j omega t, like that. Okay. All right. So, what do I want to do? I want to think about my order of doing stuff here. Okay. Okay. All right. So in general, if I have these guys right here like this, right, this is our basic form of the differential equation, right? We've got a couple of different ways to try to solve these particular things. All right. So let's kind of go through for these inputs. If I have an exponential as my input, let's say I have x of t is equal to c e to the at. All right. What we said, if I go back to my steps here, all right. If I go back to my steps and I look at the step where I solve for the particular solution, I said I use this term undetermined coefficients method, all right? So what does that mean? It's a fancy term. If I'm trying to solve that for that particular solution, that steady state solution, then the equation that I solve is this one, a n. If I say d to the n like that, what does that mean? What does that mean if I say d to the n power like that? Yeah, it's the order of the derivative, the nth order of the derivative, right? So, right like this. All the way, keep going down to a0. By p of t equals x of t. Where x, let's say in this case, is c e to the at. Okay. If this is the solution that I have, what do I guess ultimately as the particular solution? I guess a particular solution, always. And what I say is I use this method of undetermined coefficients. What do I guess? What guess should I have? Let's look at a simpler system, right? Let's say I just have dy by dt plus, I'll write it this way, a1, a0, y of t equals c e to the at. What do I guess for the steady state or particular solution in that case? What do I guess? I'm going to make a guess of some kind. What guess do I make? What's that? Constant times what? Well, everything here, let's say everything here is real. Right? It doesn't have to be, but let's just say everything here is real. Well, let me ask you this. What would happen if it was just this? What would you guess then? So in other words, I got a different, okay, just to make it simple, let's put numbers. You guys will feel better with that. Say a dy plus 3y equals 2. Okay. What would you guess in that case? What has to be true in steady state? Let me ask you this. If I have a differential equation, if I have a circuit, Okay, RC circuit. So if I have an RC circuit, I have a differential equation. What's the Y if I have an RC circuit? No. What do I solve for in an RC circuit? You guys are gonna tell me you took 2111 last semester, right?
Might be like voltage across the resistance.
Well, it'd be voltage across resistor or capacitor. Usually it's the capacitor voltage, right? So usually it's the capacitor voltage because that's the thing that it's the capacitor that's the thing that's slowing everything down. So it's the capacitor voltage typically, or the inductor current if it's an RL circuit, right? So what do I know is always going to be true about the voltage on a capacitor in steady state in the first order circuit? Not necessarily zero.
Maybe just maximum.
It reaches a constant value, right? That constant value could be zero or it could be whatever the voltage source is telling it to be, right? It always reaches a steady condition. So what's going to be true? What do I guess to be the steady state value here? Well, maybe. Yeah, I guess it to be a constant. I know that the steady value is going to be a constant, but I don't know what it is. So that's the undetermined coefficient. I need to determine it, right? So I guess that it's going to be a constant B, okay? And so what do? I plug that in here. So what do? I say d B by dt plus 3 times B equals 2. What's the derivative of the constant B? 0. Okay. So that leaves me with 3B equal to 2. What's B equal to? 2/3. That tells me that if this came from an RC circuit that had, a 2-volt, I'd have to think about what this circuit actually looked like, but it would tell me that the final value of the voltage on that capacitor would be 2/3 of a volt. All right. If I have a constant input over there, then the steady state value of the output. So I'm using term input and output. And there's a reason why we use that term. So Y is my output. So if I have an RC circuit, the voltage on the capacitor is the quote unquote output, right? If I have an RL circuit, the inductor current is the quote unquote output, right? But there's some voltage source or some current source that is the input to that system. All right, that's kind of a general way. You're going to learn that more and more of thinking about these sorts of things, but we think of things as systems that have inputs and outputs. All right, and the tools that we're learning help us to think about the connections between the inputs and the outputs. Okay. All right. So this is a simple one. You should have seen this in differential equations. If I had something fancier like this, all right. And again, it's fancy looking, but let's simplify it a little bit. Let's say I have just again a first order system like this. A1 dyp dt like that. What do I guess in this case? B e to the at. All right. Now, there's something fun about exponentials, right? You may not think there's anything fun about exponentials. I think there's something really fun about exponentials. What's nice about an exponential? Their derivative is the same as they are, right? I pulled down the exponent, but essentially it's the same. So let's just try that real quick. If I go here, and it's what's really useful. It's ultimately what allows this is actually the reason that really makes complex numbers useful to us right here is this step. And we're going to see it, more directly in a second. But let me write this a little bit cleaner. If I plug in y sub p into this thing, right, that means that I get a1 times d by dt of b e to the at plus a0 b e to the at equals c e to the at. All right. Help me simplify that for a second. What happens when I take that derivative of b e to the at? What is it? Yep. Yeah, so it becomes a1 times a times b e to the at, right? Because the derivative of e to the at is a times e to the at. plus A0 times B e to the AT. That's all equal to C e to the AT. I got a simplification I can make there, don't I? How can I simplify both sides of that expression? Oh, yeah, exactly. All the time dependence on that equation just went away, right? E to the AT, boom, boom, boom. And I basically am left with A1 times A, B. Let's get group terms real quick. Now you're looking at this going, he just wrote a bunch of algebra there. If I built this system, right? If this came from a circuit, C would be a number. A1, A, and A0 would all be numbers. The thing I wouldn't know would be B. And I would solve this thing for B, right? And if I had a second order, what would I do? In general, if this thing was nth order, I would guess that I had n. So if it was second order, I would guess that I had 2 exponentials. If it was third order, I would guess that I had 3 exponentials, so on and so forth, right? And this is a special case of that exponential where basically I just said this guy was 2 e to the 0t, right? Or 1, right? So it's basically just following the same approach. All right. We're going to solve one completely here in a second. All right, we're going to use this full approach. But let's look at this guy here. Something I want to think about because I'm going to use it a lot in these problems. It's something called a unit step function. All right. A unit step function. What is a unit step function? We're going to talk more about that stuff later. All right, but you should know what it is if you've gone all the way through 2111. What is, if you've taken it, what is U of t? Anybody know? Or you might have seen it in differential equations. It's a function that basically is U of t is equal to 0 for t less than 0, and it's equal to 1 for t greater than or equal to 0. Right? So if I graphed it, it would look like this. Right? It just goes to 1. We call it a unit step because it looks like a step, looks like a stair step, right? Jumps up at equal to 0. Now, we use this a lot because it approximates this type of a setup here. So if let's say this was a voltage source V, right? What would be the voltage here before that switch closed? What would be the voltage here before that switch closed? 0, right? Basically what would happen is when this switch closes, this voltage here would be what? V. V. All right, and I can see that by doing KVL around that loop. But V and V sub S would be the same. So this U of t approximates what a switch does in a real system, right? Which is why we use it. All right, and so we're going to use this a lot. But typically what I'm going to do is I'm going to say if I have something like this where my source is a constant times U of t, like that's exactly what this is right here. All right, a battery with a switch in series with it is A times U of t, where A is the voltage on the battery, right? Basically what that means is I'm going to think of it like this. For t greater than or equal to 0, it's equal to A, and it's equal to 0 for t less than 0. All right, that's how we're going to approach these problems. Okay. All right, so let's do a real problem. Let's say I had a circuit that looked like this. All right, so if I had a circuit like the following, where I had a single R and a single capacitor, I don't care what the R and the C values are in this particular case. But what I have is I got this differential equation. Okay. Whatever the R and the C values were got me to that. Okay. Now, notice what Y of t is. All right. Y of t is what physically in my circuit? Yeah, it's the voltage across the capacitor, right? It's always going to be that. It's either the voltage across the capacitor or the inductor current. Those are the things that you're solving for. For this class, I'm just going to call it Y because this is a math class, really. I'm just going to think of Y as the output. Okay, it's the thing I'm solving for. And my voltage source is 4U of t, which means, again, that I must have a 4-volt source and a switch that closes at t equal to 0. And so my actual x of t must be that. All right. That's what I actually physically built. Okay. All right. And I'm told this right here. I got that differential equation. What's this garbage? Y of 0 equals 10. What's that? It's my initial condition. It's my initial steady state. So I always have a starting steady state, an initial steady state, and a final steady state. All right, this is my initial one. So Y of 0 is equal to 10 volts. All right, so what we said is I got basically a three-step process that I follow here. Step one, solve the homogeneous equation. All right, that's the transient solution. Solve the non-homogeneous equation. That's the particular or the steady state. And then step three is to combine them. And I got to use that initial condition piece when I combine them. Okay. All right. So let's walk through this guy. Step one is the transient solution. So this was our original equation. That's the non-homogeneous. How do I turn that into the homogeneous equation? Set it equal to 0. So I get 0.01 dy by dt plus y equal to 0. Okay. Now I'm going to change this for a second. And I'm going to say, let's say in general, this thing was not this. Yeah, let me just say in general that this guy was equal to, this page is taking, all right, let me say in general, let's say this guy was dy by dt. I'm going to make a quick note here real quick. I call the y in this equation y sub c. All right, that's so in other words, the specific solution to the homogeneous equation, which is called the transient solution or the homogeneous solution or the complementary solution, I write it separately. And at the end, like I wrote out here, I combine the solution to be the sum of these two things. Okay. All right. So I'm solving this guy right here. Let's say in general that it looked like this, where S is some constant. I guess the solution to this guy as well. Okay. What guess do I make for this? What guess should I make? What's that? Sounds fancy when I say it this way. You already told me the answer. What's going to happen if I have a first order system, right? Starts at a steady value, ends at a steady value. What's it do in between those 2 points? It's an exponential, right? So let's guess that it's a e to the st, like that. And what am I trying to do? Let me just solve the equation I was trying to deal with. Let me not make it more general. Right? Just 0.01. Let's say it's that. I'm going to guess that. Okay. With one caveat. It would be a really dumb choice if I said A was equal to 0. All right. So A is a number. I don't know what A is. I don't know what S is. I'm going to guess A to the ST. But I'm going to make sure I guess so that A is not equal to 0. What's special about this? Well, what's special is what comes next. What do? I make this guess, right? And I plug the guess in, right? So I say I get 0.01 times d by dt of A e to the st plus A e to the st is equal to 0. What's up? Because I'm stupid, that's why. Yeah, good catch. It should be just that. All right. Right. 0.01 dy plus y equals 0. All right. So just make sure, since I messed that up, hopefully that makes sense how I got from one line to the next. Right. All right. What happens when I take the derivative of a e to the st? Multiply it by s, right? The s comes down, right? So basically I get in this case, 0.01 a s e to the st plus a e to the st. All right. That all equals 0. I'm going to put the 0 over here for a second because I want to keep factoring this thing. Right? If I keep factoring this guy, what happens? What can I factor about this equation I just wrote?
Yes.
Yeah, a e to the st comes out. And that's multiplied by what in this case? 0.01 s plus 1. Now, what I have is, this is like what I just wrote here is if I have a, b, c equal to 0, any one of those three things could be equal to 0 to make that equation 0, right? If I tell you a e to the st, only one of a e to the st times this thing equals 0. That's three things multiplying each other. Only one of those could ever be 0. Which one? Right? A, I said that would be a really stupid guess. If I said A was equal to 0 in my guess, I guess the transient was 0. It's a dumb guess. All right? Because it's not. I know that it's real. What's true about e to the st? Is that ever 0? Unless I could get all the way back to negative infinity, back sometime before the Big Bang, right? Sometime I can't get to. That thing is never equal to 0. Or t equal to infinity, I guess. Well, depends whether s is positive or negative, I guess. Either way, I'd have to get to a negative infinity or a positive infinity for this thing to ever be equal to 0. So for any real number that exists, doesn't happen. So that tells me that what has to be true is that 0.01 s plus 1 equals 0, or that s has to be what? Has to be negative. Has to be what? Yeah, negative 1 over 0.01, which will be negative 100. This thing right here, we sometimes call the characteristic equation. And the reason is because it tells us the characteristics of the response that we see. That's just trivia. I don't really care about that. It's very simple to solve this thing because I just plug this in. Most of the time, you don't even think about this part. Usually, you just jump right to looking at the equation, looking at the coefficients, and you get to that, right? Once you get used to it. One thing that's really important, basically, pretty much any real system that you ever see, S is always going to be negative, right? If S was positive, what would be true about A e to the st as time advances? It would be infinitely rising, which if I think about a capacitor, capacitors don't like infinite voltages. Inductors don't like infinite currents, right? Nature will intervene to keep that from happening. So typically, you should, anytime you are in 2112, if you don't get a negative value, or in 2111, if you don't get a negative value for that coefficient, you're in trouble. You did something wrong in your circuit analysis. All right. It should always be the case that that becomes negative. Okay. All right. So I did step one. Step one, at the end of step one, all that I determined, it may feel a little bit unsatisfying, but right now, as of right now, at the end of step one, I know that this is A e to the negative 100t. I don't know what A is. Where am I going to find A? In the steady state part at the very end. Well, not in the steady state, in my step 3. After I have the steady state and I have the transient, I use the initial condition to find what that guy is. Okay. All right. So let's keep going. Let's say I have this guy. All right. And I got to get the steady state solution. The steady state solution is y sub p. It solves that non-homogeneous equation. So what I do is I basically, I had this u of t in here, but I basically say, you know what? I only deal with the time after t equal to 0. So I say I have 0.01 dyp by dt plus yp equals 4. for t greater than 0. Those are basically two equivalent statements right there. All right. So I got rid of the u of t and said, it's just equal to 4 if I consider the times after t equals 0. Okay. All right. What do I guess now? This is just like what we considered a couple of slides back. I have a constant as my input. So if I had an RC circuit, so let's just think of it like this. For those of you that have seen this, if I had a 4-volt source like this, what would be the final value of the voltage on that capacitor? This was a 4-volt source, and I waited long enough. What would the voltage be on that capacitor?
Minus the voltage on the resistor.
That's correct in general. But if I waited long enough, what's got to be true about the voltage on that capacitor? You guys aren't giving me good feelings about 2111. Tell me you did RC circuit in 2111 if you went through it. Well, I know some of you guys are currently taking it, but I know that like roughly half of you have taken it. If you have taken it, you're going to tell me like you did it like the last day of the semester. You guys are looking like you don't really remember this at all, right? You don't have any circuits on the homeworks. Don't worry about that. I'm trying to relate it to this. If I had a 4-volt source and I waited long enough, that capacitor is going to charge up to what? 4 volts. And so the final value of the voltage on that thing is going to be 4 volts. All right. In steady state, it would be 4 volts. So I'm trying to use that to say, okay, well, if I'm thinking about the steady state solution to this guy, right, the steady state value is going to be a constant. And what I do is I just say in general, I don't know what it is. I'm just going to say it's equal to a constant. All right, so I guess that. And it's a pretty smart guess because I know that in a real system, this is what would happen. Right. So from a math perspective, this is my undetermined coefficients. I haven't determined what B is. I'm going to determine it. Right. So I plug that in. So I get 0.01 times d by dt of this constant B plus this constant B equals 4. Okay. What's the derivative of a constant? 0. So that guy's gone. And I'm left with the very simple answer, B equals 4, which is exactly what we said if I had a capacitor, the 4-volt input here, I'd eventually get the 4 volts on that thing. That's the steady state value of the voltage, right? So it's 4 volts. All right, so step 3 is that I got to this thing. And I called it C here, not A. All right, but basically what I said here is that I ended up with 4 plus a constant times e to the negative 100t for t greater than or equal to 0. Right, that's the other way of saying this. This guy is my particular solution. This guy is my transient solution, y sub c, right? And I'm setting the sum of those equal to the total value. I still don't have everything figured out, right? I don't know what this value is here. So how do I figure out what that value is? Use the initial condition. So what I said was that y of 0 was equal to 10. So I say that's equal to 4 plus c times e to the negative 100 times 0. What's e to the negative 100 times 0? 1. So 4 plus c equals 10. What's c equal to? 6. That tells me that y of t is equal to 4 plus 6 e to the negative t over 100. Well, no, sorry, t times 100. For t greater than or equal to 0. Okay. And so what does that look like? Well, it looks like this. So I got 3 graphs here. Okay. 3 graphs that I put on top of each other. You guys can look at the code. Well, we'll look at the code a little bit here. All right. 3 graphs that I drew. So without looking at these, I can't cover it up on the screen. That doesn't make any sense. Which one is which? Which one is the transient, which one's the steady state, and which one's the total solution? So the total solution being the sum of the two. Let's start with the steady state. Which one is the steady state of the three graphs that are shown here? This one, right? This is y sub p. Okay. Which one is y sub c? The blue one, right? Now, what's special about that guy? How do you know that he is that one? Goes to zero, right? With that, and e to the negative t times anything is eventually going to go to zero. This guy is the sum. All right, this is y of t equal to the sum. All right. And so I drew all three of them on here so we could see the difference. So what you'll see in the homework is I will end up giving you typically the time vector. All right. And then you guys will end up figuring out these things. So what did I do for I used the exponential function for the transient. What did I do here for the steady state? What's that thing, do you think? Ones. I mentioned it really early on, but I don't think I've made you use it for anything. Yeah, it's a vector full of ones, right? Just like a vector full of zeros if I use the zeros command, all right? For all I know, there's a threes command. I don't know, but zeros and ones exist, okay? And they're commonly used. So what I did to get y was I just added those together, all right? And I'll give you this code example when I post these, so you can see. But typically, when you enter your homework, you're going to be entering it like that. Oh, although I would expect you to be doing it by hand, like we just kind of walked through, right? Okay, so what we'll pick up with next time, because we don't have enough time to really kind of look at this. I'll start it here real quick, but let's say I had this, all right, similar circuit, but now my voltage source is a cosine, all right? Now, this is pretty common. Like I said, this is something I have all the time if I had like an audio waveform or something like that, or a power system signal, right? Is I basically have a voltage source that's a cosine function of time, and my output is y, that's the voltage across the capacitor, and I'm told that the initial value of the voltage on that capacitor is 10 volts again, okay? Now let's see if you would remember from differential equations, how would I approach getting the steady state solution to this beast? How would I approach getting the steady state solution to that? Anybody remember? What is it? I heard some mumblings over there. Well, you're right. That's exactly. I'm going to turn the cosine into a complex exponential. That's what I'm going to do, right? If I didn't know that, then what I would do is I would guess something like this. I would guess that it's b cosine 300t plus phi, right? In other words, and this is a little bit, I'm thinking of everything from a math perspective. I don't like thinking from a math perspective, all right? But I actually like thinking from as a physical perspective. If I have a circuit and I put an audio wave into a circuit, I would expect an audio wave that looks sort of the same to come out of it. Maybe it's bigger, maybe it's smaller, maybe it's shifted. Okay. One of the kind of magical things about circuits, not magical, it's any linear system, turns out. If I take a circuit and I put a sine wave into a circuit, and that sine wave, the input to that circuit is omega, all the voltages and currents have that same frequency, right? The frequency never changes. The only thing that can happen in that circuit is the amplitudes and the phases phi are going to be different from the input. If that's the case, it turns out to be really handy because it means that all that I'm going to need is b e to the j phi, which is a constant number. All right. I can simplify things a lot. I can get rid of the t part, which ultimately means I can get rid of the derivative part. Okay. That's where the stuff becomes really useful, is I can ultimately, every circuit you ever solve would be differential equations based if I couldn't use complex numbers to represent these guys. All right. The fact that I can represent I can represent these cosines as complex numbers basically allows me to use something called impedance, which you'll learn in 2112, which basically is just algebra approach rather than a calculus approach to solving things. All right. And it turns out to be a much, much simpler way to go. But if I had this, I would guess b cosine 300t plus phi. If I guessed that, so I have 0.1 times d by dt of what with that guess? So the derivative of this guy, right, plus 3 times that is all got to be equal to this. What do I, first of all, how many equations is this? It's a trick question. How many equations is this? It's 2. There's ultimately 2 in there, right? There's 2 unknowns, b and phi. Yes, it's 1 equation, but I can turn it into 2. And I can turn it into 2 by basically, ultimately what I'm going to do is I'm going to end up saying, when I look at this, I can get 1 equation that tells me the b, and I can get 1 equation that tells me the phi. And how would I expand this whole thing out? It would be ugly, right? I would have to use trig identities. I'd use a derivative. What's the derivative of cosine 300t plus phi? What's that part? That part you should know. What's the derivative of cosine 300t plus phi? Negative 300 times sine. Then I have to start breaking up the sines and cosine with trig identities. And then I'd end up making 2 equations out of it. It would take me an hour. All right. That part is ugly, right? And you can look that part up in the book as to how to do that. What we're really going to do is we're going to jump ahead and we're going to say, well, what happens if we convert this guy, b cosine omega t plus an angle, into that, right? And then actually turns out, it looks like there's a lot of steps right there, but it comes really simple. All right. And that's what we'll do on Thursday. All right. We'll stop there.